Okay, so the second part 2 of the fundamental theorem, involves some stuff we've done before. So the evaluation part is the stuff we did. That was the last thing we did last chapter. Okay, we're going to develop the concept of the other part of the fundamental theorem. So we're going to determine how to take a derivative of a function that it's an integral. Okay, so what it means is what it means to define a function as an integral. Once we can do those things, we're going to answer the big questions from this chapter, from this lesson, are questions you've been asked before. These questions I'm highlighting right now. Those things that I'm highlighting right there are questions you're going to see in this lesson. And they are questions you've been asked before in this class. Increasing, decreasing. Is a function increasing or decreasing? Is a function concave up or concave down? Are there any inflection points? You're going to be asked to find those questions. So we need to kind of dig up those notes to figure out, how do we know if something's increasing or decreasing? How do we know if something's concave up or concave down? How do we know if there's an inflection point? Okay? Because that part is not new. We've done that before. Okay, so let's start. We just took a test on doing things like this, right? So first thing we did was find the antiderivative, right? What's the antiderivative for this guy? What's the antiderivative going to be? Not the answer, but what's the antiderivative? G, right? Because it's the derivative. Well, what's the antiderivative of the derivative? G, right? So you get g of t, and then I have to evaluate it from x to 2, right? Evaluate means plug in. So I'm going to plug in x first, minus, and then I'm going to plug in 2. Right? Well, I don't know what g of x is, and I don't know what g of 2 is, so that's as far as I can go. That's as far as I can go. Okay? So let's do example number 2. What's the difference between example number 1 and example number 2? They look almost identical, but there's one key difference. What's the difference? The d over dx part, right? D over dx was not on the first part. Well, what does d over dx mean?
With respect to x?
But what does it mean? It does mean with respect to x. It means find the derivative, right? It's an action. It means find derivative, right? That's what that means. So we have to do the same thing. So since we've already done this, I know the answer to this guy. The answer to this guy is what I just did in problem number 1. So in other words, it's asking me, it was g of x minus g of 2, right? Now find the derivative. Well, what's the derivative of g of x going to be? G prime of x. What's the derivative of g of 2?
G prime.
Not g. Okay, so it could be g prime of 2, but what is that going to be? No, we don't know what g is, right? So let's say we did know what g is.
G prime of 2 times dx?
So it's going to be, you guys are right, but it's going to be a value, right? Isn't it going to be a value? So what's the derivative of a value?
0.
0. It's always 0, right? So it doesn't really matter what it is. It's just going to be 0 because the derivative is always of any value is 0. So what we just did there was showing what the second part of the fundamental theorem is. So it says, anytime you're dealing with a derivative of an integral, you're just going to stay where you're at. If I'm taking derivative of an integral, you're just going to stay where you're at, right? So essentially, that guy is just going to go there, right? That's the short way to do it. The long way to do it is the way we just did it. Okay, so there's a short way and there's a long way. Doesn't matter to me whichever way you do it, but the second theorem, the second part of the fundamental theorem says you don't have to do it that way. Okay, so let's do number 3. So g of x is an integral. They want me to find g prime. So in other words, they want me to do this. What is that going to be?
F of x.
Yeah, it's just going to be f of x. Okay. What's this guy going to be?
15t squared minus 4.
You're close, but not, you're close. So if we don't know, we can do what we always done, right? Find the antiderivative. So we're going to find the antiderivative and then evaluate. So the antiderivative of 5t to the third is 5t to the fourth divided by 4 minus 4t squared divided by 2 plus 1t. And then I have to evaluate it from x to 3. So I have 5/4 t to the fourth minus 2t squared plus t, and I have to evaluate it from x to 3. So that means I'm going to plug in x. Everywhere I see a t, I'm going to plug in an x. And then everywhere I see a t, I'm going to plug in a 3. So over here I get 5x to the fourth minus 2x squared plus x. And over here I get 5/4 times 81 minus 18 plus 3. Now I kept forgetting to write a part that I should have written. What part did I miss to write? Did I drop? In other words,
So we're d2?
yeah, the beginning, right? So I should have had a d over dx. I didn't because it just repeated itself, but I should have. Okay. So what's the derivative? What's the derivative going to be now? Can we put phones away, guys? or the next test is going to be, whew, that's going to be a doozy. Okay? So what's the derivative now? We haven't had derivatives in a while, and if we need practice, we can have some practice, but I think you guys know how to do it. What's the derivative going to be?
25 over 4x to the 5th minus 6x.
No. Let's start with this guy. What's the derivative?
4 times 5 over 4, x third to the third. And then it'll be 4x.
So this guy, wait. So the first guy is going to be what?
5 over 4 times 4, and then x to the third.
Okay, so what is it going to?
4 times 4.
It's going to be 5x cubed, right? 5x cubed, good. And then what's the next guy going to be?
4x.
4x, just 4x, right? And what's the last guy going to be?
1.
There you go. Okay. Good with that guy. That's the derivative for there. Now let's go derivative to this guy. What's the derivative this guy is going to be? Y 0. Yeah, you're right. Y 0.
Because they're all just regular numbers.
Yeah, it's just whatever it is. There's no variable there. So the derivative is going to be 0. So really, the answer to this is 5x to the third minus 4x plus 1. Now, does that look familiar at all to you? Look at the very beginning. Very, very beginning. Wasn't it right here to begin with?
Yeah.
There and there, right? So the second fundamental theorem says you can do all that work, or what I could have done was just plug in an x anywhere there is a variable, and I would have been done. Either way, it doesn't matter to me, but kind of makes your job a little easier if you can, remember that. Okay? So that's what the second theorem, or the second part of the fundamental theorem is now. So you're not going to see it like this too much. I'm going to show you how you're going to see it. How you're going to see it is on the back side. You're going to see it like this, usually associated with graphs and tables. Okay? So g of x is equal to the integral from x to -2, or from -2 to x for w of t, where the graph is w of t. I don't like how they're using different letters. I wish they use w's and x's. If it doesn't make sense to you, change like the graph. You can change that to f, because sometimes it kind of makes it hard because they use different letters. So this is a graph of w of t. That's what the graph is. Okay? It's not g of x, it's w of t. That's what the graph is. So how do I find g of 0?
You plug in the numbers to the
Plug in 0, right? Plug in 0 everywhere there's an x. So everywhere you see an x, plug in a 0. So that means g of 0 is going to equal
1.
right? I plugged in a 0 everywhere I saw an x. Now, how do I solve that guy?
Plug in.
Well, I've already plugged in things. So what do I do? How do I solve that guy? Use the graph, right? So what part of the graph am I going to use?
From 0 to -2.
From -2 to 0, what am I going to do?
The area.
Area under the curve. That's what it's asking you. It's saying go to the graph w of t and find area under the curve from -2 to 0. That's what it's saying. So we'll do that.
0.
From -2 to 0, yeah, it's actually going to be 0, right? Because it goes from here to here. So it covers this spot, that triangle, and then this triangle here. They're both the exact same size, 1 by 1 triangle. One is positive, one is negative. So this guy is going to be positive 1.5, this guy is going to be negative 0.5. Okay? If I add those two together, I get 0. So the area between g of 0 is 0. Okay. Letter B. What's the first thing I do for letter B?
Plug it in.
Plug in 2 everywhere you see an x. So again, this is asking, what is the area under the curve from -2 to 2 for the graph w of t? So from -2 to 0 is 0, so we got to go here now. So I'm going to increase in size here. Okay. So I know the area from there to there. So I know that area so far. So I just got to find the area from 0 to 2.
3.
So yeah, so I'm going to break it up into a triangle and a rectangle. So it looks like it's going to be 3 because the rectangle is a 2 by 1, so that's going to be a 2. And then the triangle base is 2, height is 1. 2 times 1 divided by 2 is 1. So you're going to have -0.5 plus 0.5 plus 1 plus 2, which is 3. So g of 2 is 3. Okay. Letter C. G of -3. -2 to -3 w of t dt. So how do I find area from -2 to -3?
You would have to make it, wouldn't you make it -1 because you got to flip the -2 and the 3 around?
Before that,
You would find the area.
is there anything? Is there anything wrong with this? The bounds, right? They're flipped, right? Lower bound is supposed to be on bottom. Higher bound is supposed to be on top. I can change that, but what do I need to do to change it?
Make it negative.
-1. Put a -1 and then flip the bounds. This is how it's supposed to be written. Lower bound on bottom, higher bound on top. I can do that now. That's just going to be from -3 to -2,
1.5
which is,
-1.5 plus the negative times the negative.
yeah, so it's going to be a negative, right? And then times the other negative that's already in the front, so it's going to be positive. So it's a trapezoid. Let's see, so -1 times, base 1 is 2. The other base is 1 times the height divided by 2. So you get -1 times, and then I think we get 3 over 2, which is -3 over 2 or -1.5. But, oops, but it's already negative, right? It was supposed to be -1.5, but because of that, because I had to switch the bounds, it's actually going to turn this guy positive. It's kind of a double negative. I had to flip the bounds, and it was below, so that's a double negative. Okay.
-2 minus negative or plus negative.
Yeah, so what I do for those is I just remind myself that it needs to be a positive answer. So I do the problem regularly and then just change it at the end. Yeah. Okay. All right. So now we're going to do the same thing with a different graph. So what I want you to do first is fill out the table. I'll do the first one with you guys. Just to get you guys going, I'll fill out the table with you guys. So the first one, again, we have g of x is equal to the integral from -1 to x for f of t. And then f of t is the graph. So this is f of t. So to find the first guy, the first guy is g of negative 3, right? I'm going to plug in negative 3 everywhere I see an x. From negative 1 to negative 3. Well, from negative 1 to negative 3, I got to go left. I can't go backwards in time. So I got to flip the bounds. I can only go forwards in time. To go left, that's going backwards in time. I can't do that. I can only go right. So to do that, I have to flip the bounds. So I'm going to flip the bounds from negative 3 to negative 1, just like we did on the last problem. So I got to go area under the curve from negative 3 to negative 1. So this guy and this guy here.
It would be 0.
So it would be 0, right? Doesn't matter if it's a negative 1 because it would just be negative 1 times 0. So I think the area here is 1. Let's see, 2 times 1 divided, yeah, and negative 1. So it's going to be 0. So what I want you to do is fill out the rest of the table. Fill out the rest of the table. The rest of the table is the hard part. That's the new part. Everything else you've done before. Look at the next question. Increasing, decreasing. You guys have done that. Okay? So what I want you to do is fill out the table. Do the rest to fill out the rest of the table. Because the better you do with the table, the easier the next steps are going to be. Mm-hmm. So if something, anything, is increasing or decreasing.
The slope,
What about the slope?
if it's
Negative or positive?
negative or positive,
Okay. So G, how would I write that?
G is increasing from or decreasing from negative 3 to negative 1 because the slope is negative?
No, you're close. You're kind of all over the place. So G, you said slopes, right? And what goes, I'm sorry, what goes with slopes?
Positive and negative?
No.
Like mx plus b?
No. So slopes could mean a lot of things, right? So I put on the board kind of what we used last semester. So if I say slopes, that could mean a lot of different things. So my question is, how do I know if G is increasing or decreasing?
You would have to find the derivative of g and then see if it's positive or negative.
Okay, so now we're talking. So the derivative of G, right? G prime. Is positive, it's increasing. Negative, decreasing. Good. Now my next question. How can I look at the graph or the table and know where it's increasing or decreasing?
Look at the y value.
So why the y value? You're right, Isaac. You're absolutely right. Why? So let's start with G. G's at the top of the heap. What is G? What does G represent?
And when it crosses the slope.
No, I'm not talking about on the graph. I'm talking about the actual equation here.
Oh, it's
Okay. But they're all functions, right? All of these guys are functions. What makes G separate from the rest?
G is the entire area under the curve.
There you go. G is the top of the heap, area under the curve, right? G represents area under the curve. So what does its derivative represent?
Area of the curve.
No. We're up here, right? Slopes is second derivative. So what do I mean by the graph? Isaac said it earlier.
The y value?
The y values. So the y values are where I want to look for g prime. Okay? G prime. So G represents area under the curve. Area, which you did on the table. Its derivative represents y values on the graph. What do you think the second derivative is going to represent? Slopes, there we go. So we want to know where its y values are greater than 0 and less than 0 for this question. So where on the graph are the y values greater than 0? From where to where? Start with -3. From -3 to where?
-2.
There you go, right? Right there. Everywhere else, it's going to be decreasing. Yeah, it's going to be considered decreasing, yeah. Okay. So let's write this down. G of x is increasing from -3 to -2 because, and what's our justification?
The y values are positive?
Close. Something is positive. What's positive?
That,
There you go, right there. G prime of x is positive. G of x is decreasing from -2 to 3 because G prime is negative. There you go. Okay. All right. So we've done all this before, but under different lenses. We never start up here. Last semester, this level never existed. Area under the curve didn't exist. We started here, right? We started here. Okay? So now we added a level to the top, but it's the same idea. It's the same idea. Okay? All right, let's go to the back side. Let's go to the back side. It's the same table. It's the same table. So fill out the same table you fill out on the front side. So it's 0, 1. I put it up here just so you didn't have to keep flipping back and forth because we're going to need the table in a little bit. So it's the same table, just I wrote it on this page too so you don't have to flip back and forth. Okay? All right, so now concave up, concave down. So give me a reminder.
These slopes, those are positive and negative?
it's the,
What's the justification? I'm not telling, you're telling me how I'm going to find it. I need the justification. What's the justification for concave up or concave down?
it's when the third derivative
No.
G of x is positive or negative.
Not the third derivative. Second derivative, right? Second derivative. When the second derivative is positive, going back to last semester. Concave up. When the second derivative is negative, concave down. Those rules are the same rules for this semester. I'm not changing any of those rules. Okay? Now, how we find those is what Seth said. Seth said we're going to use slopes. Absolutely. We're going to use slopes. So we're going to find where the slope is positive and where the slope is negative. Okay? So we're going to go back up to the picture. Let me erase it because we're looking for the second derivative now. So the slope is positive. Oh, sorry, slope is negative here, right? Going downhill. And here, going downhill. But it's positive here. Oops, I want to use a different color. Okay. So, concave up, -1 to 0, the green. Okay, so let's write this down. Concave up, from -1 to 0. Because, use your justifications right there, right? G double prime is positive. Concave down from everywhere else. -3 to -1. Or 0 to 3. Because G double prime, is negative. So the justifications are the same justifications that you used last semester. Let's see if I can find them.
Wasn't the justification we used last semester was a change from negative to positive?
Yeah, that's the next one. That's some of the ones we haven't talked about yet, yeah. Where are my justifications? There we go. All these justifications that we used last semester are still the same justifications. Relative max, relative min, we haven't talked about, which we're going to do on the next one. Increasing, decreasing, point of inflection, concave up, concave down. You see all of these guys are exactly the same. These are not, because that's if you're looking at the derivative graph. But the justifications are exactly the same. Okay? So now the next one is maximum minimum. So how did we know if something had a maximum or minimum?
The third derivative is positive.
Because the derivative switches signs. The derivative switches signs, either from positive to negative or negative to positive. So if it's max, the derivative, so in our case, it's going to be G prime. G prime switches from positive to negative. And minimum is the opposite. These are straight from your notes. Okay? So this case, it's going to be G prime switches signs from negative to positive. Over here, G prime switches signs from positive to negative. Those are our justifications. So when we're talking about the graph, where do we look for G prime? Where is G prime going to be on the graph?
Y values?
The y values, good. So in other words, we're looking for when the y values change signs. So where do the y values change signs?
On -1 and 0.
No.
-2.
-2 is one of them, and 0 is another one. The y values were positive before -2. Afterwards, they became negative. And then it did, here's the thing. I've seen it considered both ways. It did change signs from negative to 0, right? Because 0 doesn't have a sign. But it didn't keep going. So let me check my notes. Did they consider this one? No, so they don't consider this one. Because It did change signs. It went from negative to 0. That's changing signs. But it didn't change to positive. So it has to change from negative to positive or vice versa. So this guy at 0, it's not gonna be a relative maximum or minimum. Because it has to change signs from positive to negative or vice versa. So that guy there, what did that change signs from? Positive to negative or negative to positive?
Positive. It's a maximum.
So that's a maximum. So relative maximum at x equals negative 2, what is it? Negative 2, no, yeah, negative 2. Because g prime of x switches from positive to negative.
And there's no relative minimum.
There's no relative minimum because it never switches from negative to positive. It just switches from negative to 0, and that's not good enough. So no relative minimum. Because there is a switch, but it's not from negative to positive. It's from negative to 0. Okay, 2 more, we're done. We'll do E and F, and then we'll be done for today. Points of inflection. What was our justification for points of inflection? Don't read the bottom, just read the what was the justification?
When it switches signs.
What, not switches signs,
When it equals 0.
when the second derivative equals 0. When the second derivative equals 0. So in our case, g double prime equals 0. So where is that going to be on the graph?
When the slope is going straight.
When the slope is 0. When the slope is 0. When slopes are 0, that's when it's going to be. Or sorry. Yeah, you're right. It still switches signs, right?
It says right there, really. It said when it switched signs.
Yeah. No, yeah, you're right. You are absolutely right. When g double prime switches signs. So in other words, when do I change from increasing to decreasing or vice versa?
-2 and 0.
So here we go. Let's start on the path. I'm going negative. When do I switch to positive? When do I switch to increasing?
-1.
So -1 is a first spot. Where else?
And then 0.
0. I keep going. So -2 and 0.
I mean -1.
Yep, -1 and 0. Sorry. Yep. -1 and 0. So here we go. Let's see. Let me write it over here. Points of inflection at x equals -1 and 0. Because g double prime switches signs. G double prime switches signs. Okay.
And draw the graph.
So how do I graph g of x?
Putting all the different.
So let's start. Where would the first point be?
0.
-3, 0, right? -3, 0. Isn't that the table for g of x? So just make those dots. -3, 0. -2, 1. -1, 0. 0, -1. 1, -1.5. 2, -3. 3, -5.5. So this is a graph of G. So in other words, it's a graph of the areas. Graph of areas under the curve. That's what it is. So you can see when is the area, what is the absolute, so there's another question. What's the absolute max area that I have? 1, right? The biggest my area is going to be is 1 when x is -2. What's the absolute minimum area I will have? -5.5. At 3, I'll have an area of -5.5. Okay? So the big part of today has to do with what we did last semester towards the end. How do you know if something's increasing, decreasing, relative maximum, minimum, concave up, concave down? All of those justifications. Okay? All of those justifications. All right. All right, we'll stop there for today, and then we'll do the next problem